Welcome back everyone. In this lesson, we are going to look into a single area OSPF version 2. In this lesson, we will look at how to configure OSPF. So this topology that you see here will be used to describe OSPF configuration. So it is good for you to have this topology in Packet Tracer so that you can actually follow step by step as we go on with the configuration. So pause the video for a while, go to Packet Tracer, build this topology, and then come back and continue. So within this topology, we would see that there are 3 routers within the network, and if you see the color here, they are within the same area, area 0, and then R2 is connected to their internet. OSPF version 2 configuration uses the router OSPF configuration mode. This is similar to every other dynamic routing protocol configuration. So in the configuration mode, you type router OSPF and the process ID, in this case 10. And then when you enter, this will bring you to the router configuration mode of OSPF. Of course, if you type a question mark, you can see what other commands that is available within this prompt. Router IDs are used to uniquely identify an OSPF router. So router IDs here are 32 bits long in both IP version 4, which is OSPF version 2, and OSPF version 3, which is used for IP version 6. The router ID is used in the election of the DR, designated router, if a priority number is not configured. Remember again, what is the purpose of a designated router? It will be sort of like a distribution point for every other router within the topology so that they don't use so much bandwidth for updates. So ways a router gets a router ID, if you look here, is very similar to EIGRP. These are ways a router gets a router ID. One, by manually configuring the router ID using the router ID command. Secondly, if the router ID is not configured and there is a loopback, the highest configured loopback interface is used. If there is no router ID configured, there is no loopback used, then the highest active IP version 4 address is used. If you notice, the router ID configuration is under the router configuration, and in this case, it is the OSPF router configuration. So router ID and whatever ID you want to give it. In this case, for router 1, they decided to give the ID 1.1.1.1. Now, once you do that, you see here the router is telling you what it is doing. So it is telling you that it has configured from console by console. So this particular whatever you did was actually done. And you can verify this through show IP protocols. If you go down, you would find router ID 1.1.1.1. If, for example, initially when you start configuring your network, you didn't configure router ID. Now you want to modify the automatic router ID into something that you want to manage. To make sure that the new router ID is taken and used, it is good for you to use the command clear IP OSPF process. What it does is that you can imagine this process is clearing whatever you wrote before and using the new value. And now you would see that the new value has been adopted. Using a loopback interface as the router ID, this happens in iOS versions that did not have router ID OSPF configuration command. Okay? Loopback interfaces were used to provide a stable router ID. Now, loopback interfaces are virtual interfaces that does not go down. If you type shut down, it will shut down. Other than that, it is always active. So now we go into enabling OSPF on interfaces. So here we use the network command to specify which interface participate in the OSPF version 2 area. So now we have an area and which network will provide or will participate in that. So again, we have router OSPF process ID. And then once you get into the router configuration mode, you type network, which is the network address here. network followed by network address, the wildcard mask, the area, and then the number area or area ID. If a single area topology is used, it is best to use area 0. A common misconception, R2 has 3 interfaces in area 0, so 3 network statements are used, not 6 network statements. Now, if you notice from EIGRP and RIP, when you want to type down the network statement, you type the network statement that is directly connected to the router, the network that is connected or owned by the router. You don't go and do the neighbor's network. For example, here for R2, we would have this one, and that one in one area. But you don't do this network because it has nothing to do with R2. You report what you know. Let's look back at wildcard mask. Okay, to determine a wildcard mask, subtract the normal mask from the 255.255.255.255 address. Okay, so a wildcard mask bit of 0 means match the bit. A wildcard mask bit of 1 means ignore the bit. So here you will see a /24 and then 255.255.255.255 minus 255.255.255.0, which is /24, and then this is what you get for the wildcard mask. So if you remember, wildcard mask is sort of like the opposite of subnet mask. So here the subnet mask is /26 and the wildcard mask you get 0.0.0.63. There are 2 ways to use the network command. One is the traditional method where you have the network address and the wildcard mask and then you put in the area. Method 2, you can use the IP address of the interface and 0.0.0.0. 0.0.0.0 here means specifically these bits, exactly those bits. If it's 1.2, it doesn't work, only 1.1. So every bit must follow this and then area. Now, some students like this because you don't have to think. You just look at the IP address and then you just put it in. But you as future network administrators, you need to know both. Why do you need to know both? Because when you go out into the real world, you do not know how that particular organization or that particular company runs their network. So you cannot go there and say, I really don't know how to do this. I only know how to do this. So you have to have knowledge. Okay? How you apply your knowledge is up to you, but knowledge you should have. Again, passive interface. We have seen this many times before. You know what it is. It is an interface that you don't want to send routing updates to. They don't need it, so we don't want to waste bandwidth. So we set those interfaces as passive interface. So here, in this example, all the LANs of the routers are set as passive interface. Configuring passive interface is the same. You type passive interface, gigabit Ethernet 00. This is the interface that you want to make passive. So in this case, you just put gigabit 00 in R1, gigabit 00 in R2, gigabit 00 in R3. And then to verify that what you did already is correct, go into the show IP protocols and you will find, oh, there you go, the passive interface is there. Okay, verification is important to make sure that your work is correct. Sometimes, we type A, but then it's actually S. Sometimes we type 1, but then we click on 0. So these are things that we might subconsciously do, and it's always good to check. Checking your work is the best form of troubleshooting rather than trying to find a needle in the haystack when a problem occurs. Let's talk about metric. OSPF uses cost to determine the best path to a destination network. Cost is given by a reference bandwidth divided by the interface bandwidth. The lowest cost is a better path. The interface bandwidth influences the cost assigned. The lower the bandwidth of the interface, the higher the cost. So if you look at this table, An interface running at 64 kilobits per second serial, it has a cost of 1,562. A 10 megabit per second Ethernet interface has a cost of 10, and then 10 gigabit per second Ethernet has the cost of 1. We have a problem here because these three different types of interface with different capabilities all have the same cost. This is an issue when you look later when you want to find the best path. Looking at the table, you know this is the best. But then again, all of them have the same cost. So we can adjust this. The cost for a destination network is an accumulation of all the cost values from source to destination. The cost metric has been seen in the routing table as the second number within the brackets. So here in the routing table, this is the administrative distance and this one is the cost or the metric. Okay, and if you look here, going from this network to this network, you have this one, which is the cost is 64, and then from here to there, the cost is 1, and the total cost would be 65. So it is an accumulation, a collective amount of cost from source to destination. Changing the OSPF reference bandwidth affects only the OSPF calculation used to determine the metric, not the bandwidth of the interface. So if you change it, it doesn't automatically make your bandwidth higher or lower. It just changes the cost that you attach to it. Use the AutoCost reference bandwidth command to change the OSPF reference bandwidth. As we saw before, these three have the same cost. Because the reference bandwidth is the same, and even if you divide it by this, you will get the same cost. Adjusting the reference bandwidth, here is an example of how we adjust the reference bandwidth between megabit per second Ethernet to gigabit Ethernet. Let's put a gap of 1000 between megabit Ethernet and gigabit Ethernet. If we see here, there is a difference now between megabit Ethernet and gigabit Ethernet, but we still have the problem that these two, 1 gigabit, 10 gigabit has the same cost. So we can adjust to 10,000 and then we would see a difference here. If the routers in the topology are adjusted to accommodate gigabit links, the cost of the serial link is now 647 instead of 64. The total cost from R1 to R2 LAN is now 648 instead of 65. So if we use the adjusted value from just now, you would see that it has now increased on this part. And the total cost would have increased as well. If there were fast Ethernet links in the topology, OSPF would make better choices. Bandwidth values defined on an interface do not change the capacity of the interface. These bandwidth values of an interface are used by EIGRP and OSPF routing protocols to compute the metric. So serial links by default has 1.544 megabits per second, and that might not be an accurate bandwidth for the transmission rate. You can use the show interfaces command to see the interface bandwidth. So here, show interface serial 000 of R1, you'll find the bandwidth is 1544 kilobit per second. And here, you would see the interface of 001 of R1. It has the bandwidth of 1544 kilobits per second. So when you do the show IP OSPF interface serial 00, so you're now wanting information about OSPF as well. So here you have the serial and information about the serial, and then it also has the cost, meaning that this particular interface here has the cost of 647. So if you want to adjust a specific bandwidth for a specific interface, you go into the interface and use the bandwidth command. Okay, simple enough. So now the interface of 001, which was 1544 before, is now 64 kilobit per second. And when we show IP OSPF interface of that particular interface to include cost, you will find that the cost has risen. Okay, we have made the bandwidth lower, the cost will go higher. The bandwidth must be adjusted at each end of the serial links. Therefore, R2 requires its serial 001 interface to be adjusted to 1024 kilobit per second. R3 requires its serial 00 to be adjusted to 64 kilobits per second. And its serial 001 to be adjusted to 1024. So once you adjust in one router, you have to make equal adjustment on the other side. Okay? Because you don't want one to say this is a bad route and then the other to say this is a good route. So you have to adjust it. And when you want to adjust bandwidth, please do this carefully. You should understand your topology. You should be a master of your topology. You know where you want to route things, and then only then you apply the bandwidth command. If you are not sure, it is best not to touch this until you have experience. So besides using the bandwidth to adjust the cost, you can also configure the cost manually using the IP OSPF cost value. So here you would have changed the bandwidth, and when you change the bandwidth, it automatically changes the cost, or you can directly change the cost to a cost that you want. If for some reason you have typed the bandwidth and now you want to change it, just type no bandwidth 64. So no is a very good command to know. Now we are going to learn how you verify who your neighbors are. Show IP OSPF neighbor. So this will show you who your neighbors are. So this is done in R1. So who are the neighbors of R1? We have R2 and we have R3. So here neighbor ID tells you the router ID of that neighbor. Okay, we have changed router 2 to 2.2.2.2 and router ID for router 3 has changed to 3.3.3.3, and this is the router ID. Priority here is the priority of the interface to be used in DR-BDR election process. So in this case, both of them have the same priority. State is the different state that the router is in. Okay, so state here is the OSPF version 2 state. Full means that the linked state database has had the algorithm executed. The neighbor router and R1 have identical LSDVs. Ethernet multi-access interface may show as two-way. The dash indicates that no DR or BDR is required. Remember, DR-BDR is only done in certain types of topology, like NBMA. Okay? In this topology, it is not done. It is not used. So, there is nothing there. This indicates that it is not required. Dead time is the amount of time remaining before expecting to receive a hello packet from the neighbor before declaring the neighbor down. This value is reset when a hello packet is received. So this is how long you are going to wait before declaring your neighbor down. But if before this timer is up, you receive a hello or a notification, then this one will be reset to the initial value again. Address is the address of the neighbor's directly connected interface, meaning that you are connected to router 2 and the router 2 means that you are connected to the router through interface serial 00 and then its IP address is 172.16.3.2. Interface is the interface R1 used to form an adjacency with the neighbor. So if you see here, R2 is connected via serial 0 of R1. R3 is connected via serial 1 of R1. The show IP protocols command is used to verify OSPF version 2 process ID, router ID, networks being advertised by the routers, neighbors that are sending OSPF updates, and the administrative distance, which is 110 by default. So for you to know what is going on, you can do this command and then look at whatever it is there. To verify OSPF process information, you can use the show IP OSPF command. Okay, and if you type here show IP OSPF, it will tell you the process ID, which is 10, the router ID, which is 1.1.1.1, and then it will tell you a lot of information regarding that. Okay, to verify OSPF process information, you can use the show IP OSPF command. It will show you the process ID and the router ID and all other information regarding the OSPF of that particular router. Use the show IP OSPF interface command to see details of every OSPF version 2 enabled interface, especially to see if the network statements were correctly composed. So this is a quick way for you to check whether or not you have keyed in or input the right addresses. Use the show IP OSPF interface brief to show everything in a more brief. Use the show IP OSPF interface brief command to see key information about OSPF version 2 enabled interfaces. Use the show IP OSPF interface brief command to see key information about OSPF version 2 enabled interfaces on a particular router. So in this example, R1, so it has 3 interfaces here, and then this particular interface is the DR. This state is point to point, so the DR BDR doesn't happen, but it has one here. Okay, and since it is the only one going to that LAN, it is the DR. And then we have the IP address, we have the process ID, and so on. That is the end of this particular lesson. You will find that you have a task that you need to do. I have uploaded it to e-learning. Please do that task. It will help you with your understanding. Also, review this slide at least twice. Go through the packet tracer of the examples to follow what they did. So I'll see you in the next lesson. Goodbye.